Something broke the rules on October 3rd, 2025. Not loudly, not with fanfare or warning sirens, but quietly, in grainy images captured by a rover sitting alone on the rust-red surface of Mars, staring up at a sky humans have never breathed. What Perseverance's cameras caught that day was supposed to be routine, a faint smudge of light, an interstellar visitor passing through our cosmic neighborhood. But then astrophotographer Simeon Schmaus did something simple. He stacked 20 of those frames together, layered them like transparent sheets held up to the light. And there it was. Not just a smudge anymore, but confirmation. 3I Atlas, exactly where mathematics predicted it would be. Here's what doesn't make sense. That same day, NASA furloughed 15,000 employees. Budget cuts, they said. Necessary restructuring. But the Mars Reconnaissance Orbiter, with its high-rise camera, capable of resolution 30 times sharper than Perseverance could ever achieve, hung in perfect position above the red planet. The European Space Agency's Mars Express watched from a different angle. ExoMars Trace Gas Orbiter, specifically designed to analyze atmospheric composition, had a front-row seat to what should have been the observation of a lifetime. These machines, built for moments exactly like this, positioned perfectly to capture an interstellar object in unprecedented detail, went silent. Where are those images? Why do we have a grainy, stacked composite from a rover's navigation camera, but nothing from instruments designed to see what rovers cannot? The silence isn't just strange, it's coordinated, it's deliberate. And beneath that silence, something even stranger. 2 months before those October observations, before the closest approach, before the world even knew to pay attention, remote viewers claimed they'd detected technology aboard this object. Not ice, not rock, technology. The void between stars is not truly empty. It breathes, it carries whispers. And sometimes those whispers arrive at our doorstep wearing the mask of ice and stone. On July 1st, 2025, when automated telescopes in Chile registered an anomaly moving through the constellation Corona Borealis, no one suspected they were witnessing the beginning of something that would shake the foundations of our understanding. The object was designated 3I Atlas, the third confirmed visitor from interstellar space, a fragment of another stellar system that had traveled for perhaps millions of years to reach our cosmic neighborhood. But this was no ordinary comet drifting on predictable gravitational curves. From the moment its trajectory was calculated, from the instant spectroscopes began dissecting its light, 3I Atlas revealed itself as something profoundly different, something that did not fit the comfortable categories we'd built to explain the universe. Its chemical composition defied expectations. Its behavior suggested complexities that natural processes struggle to explain. And the pattern of what we're being shown versus what's being withheld suggests that someone, somewhere, has decided we're not ready for the full truth. What makes a comet impossible? What turns a chunk of frozen matter into a question that keeps scientists awake through long nights, staring at data that refuses to settle into familiar patterns? Perhaps it begins with the silence, the deliberate, coordinated silence that descended when the most capable instruments in our arsenal were perfectly positioned to observe this visitor. Or perhaps it begins earlier, in August, when remote viewers, those controversial practitioners of consciousness exploration, claimed to detect something aboard this interstellar wanderer. Technology, they said, not natural, not random, intentional. The rational mind recoils from such claims. remote viewing occupies that uncomfortable space between documented Cold War research programs and fringe pseudoscience, neither fully validated nor completely debunked. Yet what followed their reports was a cascade of scientific anomalies that mirrored their impossible conclusions, as if the universe itself was confirming what consciousness had glimpsed before instruments could measure, as if 3I Atlas carried within its frozen shell not just exotic chemistry, but perhaps something more deliberate, something that had traveled across the light years with purpose we're only beginning to suspect. Close your eyes now, if you wish. Let your breathing slow. We're going to walk through this mystery together, piece by careful piece, in the gentle way that allows understanding to settle like snow. No sudden movements, no jarring revelations, just the steady accumulation of facts that don't quite fit, observations that whisper rather than shout, patterns that emerge only when you're patient enough to watch them form. By the time dawn touches your window, you'll understand why 3I Atlas represents more than scientific curiosity. You'll understand why some call it a warning, and why others wonder if we're being tested. The discovery itself seemed routine at first. The Atlas survey, that tireless robotic sentinel scanning Hawaiian skies for potential Earth-threatening asteroids, caught the faint glimmer of something moving against the stellar backdrop. To the automated systems, it was just another transient object, catalogued and measured with algorithmic precision. But when human eyes examined the trajectory calculations, when astronomers traced the path backward through time and space, the routine evaporated into something stranger. This object wasn't bound to our sun. Its velocity was too high, its path too open. The mathematics described a hyperbola, that geometric signature of something just passing through, a visitor rather than a resident. Comets from our solar system's distant Oort cloud follow immense ellipses that return them again and again over millions of years. But 3I Atlas followed an arc that would bring it once through our inner system before casting it back into the interstellar void, never to return. The speed alone told the story. This fragment had been ejected from another star's gravitational domain, hurled into the darkness by violence we can only imagine, drifting for an eternity before chance brought it near our sun. Or was it chance? That question began circulating in quiet conversations long before it appeared in any official report. The trajectory was hyperbolic, yes, but with subtle deviations that didn't match standard cometary outgassing models. Small adjustments, barely detectable, that seemed to occur at intervals too regular to be random. Natural comets sublimate ice chaotically as sunlight warms different surfaces, creating unpredictable thrust vectors that alter their paths. But 3I Atlas showed course corrections that felt almost deliberate, as if something within its frozen structure was making choices, responding to conditions, guiding itself along a path that served purposes beyond simple gravitational mechanics. The first genuine alarm bells rang not from the trajectory, but from the chemistry. When the James Webb Space Telescope turned its infrared gaze toward this interstellar visitor in late July, astronomers expected to find water ice, the universal substance that dominates comet composition throughout our solar system. Water creates the spectacular tales we associate with these ancient wanderers, sublimating under solar radiation to produce the characteristic coma of gas and dust. But JWST's spectroscopic analysis revealed something deeply troubling. 3I Atlas's atmosphere was drowning in carbon dioxide. The ratio was staggering. 8 molecules of CO2 for every single molecule of water vapor. That number, measured with JWST's exquisite precision, sits so far outside the range of any comet previously observed that it demanded explanation. Carbon dioxide does exist in solar system comets, certainly, sublimating at lower temperatures than water ice. But this level of dominance? This suggested either formation conditions radically different from anything in our Sun's planetary nebula, or something else entirely. Something that might choose carbon dioxide for reasons we don't yet understand. Think about what carbon dioxide represents in technological contexts. It's a product of combustion, of respiration, of industrial processes. It's what our machines exhale, what our bodies release. While natural processes absolutely can concentrate CO2 in cosmic ice, the extreme ratio combined with everything else about this object created an uncomfortable resonance. The kind of resonance that makes scientists avoid eye contact in meetings, unwilling to voice thoughts that might damage careers built on careful rationality. But the thoughts persisted anyway, whispered in hallways and encrypted messages. What if this wasn't entirely natural? The polarization measurements deepened the mystery in ways that made veteran astronomers question decades of experience. When light scatters off dust particles in a comet's coma, it becomes polarized in characteristic patterns that reveal the size, shape, and composition of those particles. Every comet has a polarization fingerprint. 3I Atlas's fingerprint matched nothing in our comprehensive databases. The negative polarization branch, measured independently by multiple observatories from Chile to Spain, plunged to depths never before recorded. At a phase angle of 7 degrees, the polarization reached negative 2.7%, a value so extreme that papers describing it use the word unprecedented multiple times. What does unprecedented polarization mean? It means the dust particles in 3I Atlas's coma scatter light in ways we've never encountered before. Not in any asteroid, not in any comet, whether from our solar system or from 2I Borisov, the previous interstellar visitor. The dust properties suggest either formation under conditions so exotic our models can't capture them, or materials that don't form naturally through cosmic weathering and accretion. Some researchers quietly compared the signatures to trans-Neptunian objects, those distant frozen worlds beyond Neptune where exotic ices might survive. But even that comparison felt inadequate, a grasping for familiar categories when faced with something genuinely alien. And then came the water detection, which should have been reassuring but instead added another layer of strangeness. The Swift Observatory, using ultraviolet instruments designed to catch the violent deaths of distant stars, detected hydroxyl emission from 3I Atlas. Hydroxyl, that telltale signature of water breaking apart under solar radiation. The calculations suggested the comet was releasing approximately 40 kilograms of water every second at a distance of 3.51 astronomical units from the Sun. That's beyond Mars' orbit, out where solar heating is weak, where water ice typically remains frozen and dormant. Most comets don't become active with water production until they swing much closer to the inner solar system. Yet here was 3I Atlas, vigorously outgassing water at distances where it should be quiet. The models suggested at least 20% of its surface was actively releasing volatiles, an extraordinarily high fraction. Most comets show activity concentrated in a few percent of their surface area, localized jets and vents. But this visitor was breathing across its entire body, as if something internal was driving the process, something beyond simple solar heating. The brightness measurements from the SOAR telescope in Chile added another puzzle piece. Photometry, the careful measurement of how bright an object appears over time, typically reveals rotation patterns and outburst activity in comets, but 3I Atlas remained eerily stable. Its magnitude measurements in late July showed only modest brightening, 1814, then 1755, then 1754, over several nights. No dramatic outbursts, no sudden flares, just steady, controlled activity that suggested equilibrium rather than the chaotic volatility common in comets making their first close approach to a star. Stability in a comet is almost as strange as chaos would be expected. Natural objects subjected to rapidly changing thermal conditions as they approach the sun typically respond unpredictably. Ice sublimates unevenly. Dust lifts off in bursts. Subsurface pockets of volatile material find pathways to the surface and explode outward. Yet 3I Atlas maintained remarkable composure, as if its activity was modulated, managed, controlled by processes that natural thermodynamics alone cannot explain. The word control makes scientists uncomfortable. It implies agency, intention, design. But sometimes the data forces uncomfortable language. By late summer, the astronomical community had accumulated enough observations to be certain of one undeniable fact. This was not a typical interstellar visitor. It wasn't following the script written by 2I Borisov, that relatively well-behaved comet that arrived in 2019 and departed without challenging too many assumptions. 3I Atlas combined anomalies that, taken individually, might be dismissed as rare but natural variations. But taken together, they formed a pattern that resisted natural explanation. Every measurement opened new questions. Every analysis revealed fresh impossibilities. And then came October, when geometry aligned perfectly for the observation of a lifetime. 3I Atlas would pass within 29 million kilometers of Mars on October 3rd. From Earth's perspective, the comet sat frustratingly close to the sun's glare, difficult to observe without specialized equipment and careful timing. But from Mars, the view would be clear, unobstructed, perfect. The armada of spacecraft orbiting the red planet, NASA's Mars Reconnaissance Orbiter with its powerful high-rise camera, ESA's Mars Express, and ExoMars Trace Gas Orbiter with their suite of scientific instruments, all position themselves for what should have been comprehensive documentation of an interstellar object at unprecedented resolution. The anticipation in the scientific community was electric. Finally, after months of ambiguous data and uncertain measurements, they would get definitive images. HiRISE could resolve features as small as 30 centimeters on Mars's surface from orbit. Turned skyward, it promised to reveal nuclear structure, surface features, perhaps even details that would settle the question of 3I Atlas's nature once and for all. The Trace Gas Orbiter, designed specifically to analyze atmospheric composition with exquisite sensitivity, would measure the comet's coma in ways that Earth-based telescopes could never match. This was the moment when clarity would replace speculation. And then, silence. Not the comfortable silence of data being carefully processed and analyzed. Not the patient silence of scientists double-checking their calculations before publication, but the heavy, deliberate silence of information withheld. The Perseverance rover's navigation camera. Images appeared in the public archives within hours, as NASA policy requires. Raw, unprocessed frames that showed the Martian horizon, and somewhere in that star field, a faint presence that astrophotographer Simeon Schmaus would later enhance and confirm. But the high-rise images? Nothing. Mars Express observations? Silent. ExoMars Trace Gas Orbiter spectroscopic data? Absent. Days turned into weeks. The astronomical community, accustomed to relatively open data sharing among space agencies, began asking questions. Where were the high-resolution observations? Where were the spectroscopic analyses that would reveal the comet's composition in detail impossible from Earth? The official channels offered no explanations. No press releases announced successful observations. No preliminary findings appeared on the preprint servers where researchers typically share results before formal peer review. The silence felt deliberate, coordinated, as if decisions had been made at levels far above individual research teams. The timing of the furloughs haunted the entire situation. 15,000 NASA employees told to stay home on October 3rd due to budget constraints and political impasses over appropriations. The headlines blamed congressional gridlock, the eternal tension between ambitious exploration programs and fiscal reality. But the date, that precise date when humanity's most capable orbital cameras were positioned to capture history, when instruments designed for exactly this kind of observation had their perfect opportunity. That's when operational capacity was suddenly reduced. The coincidence strained credulity. Conspiracy theories crystallized almost instantly, as they always do when information gaps appear. Perhaps the images showed something that couldn't be released, something so extraordinary or disturbing that disclosure was deemed too dangerous. Perhaps the observations failed entirely, and admitting technical failure after years of mission planning was too embarrassing. Perhaps there was no conspiracy at all, just the mundane tragedy of budget politics happening to align with cosmic significance. But humans are pattern-seeking creatures. We connect dots into pictures. And when those dots suggest intentional concealment, we cannot help but wonder what's being hidden. Let's consider what should have been visible if everything went according to plan. The high-rise camera, with its half-meter aperture telescope and advanced CCD detectors, can distinguish objects as small as a kitchen table on Mars's surface from hundreds of kilometers above. Pointed at 3I Atlas from a distance of 29 million kilometers, it should have resolved the nucleus clearly, revealed surface features, shown whether this object was a rough, irregular chunk of ice and rock, or something with more geometric regularity. The resolution wouldn't be perfect, not spacecraft-quality close-up, but far superior to anything Earth-based telescopes could achieve through our planet's distorting atmosphere. Mars Express, while less powerful than MRO, still carried high-resolution cameras and spectrometers capable of detailed observations. The spacecraft has been operating since 2003, a veteran of Mars exploration with a track record of reliable performance. It had clear line of sight to 3I Atlas during the October approach, unobstructed views that Earth-based observers could only envy. The data it should have collected would have been invaluable for understanding the comet's true nature, yet nothing from this mission has been released to the public or even to the broader scientific community. But it's the ExoMars Trace Gas Orbiter that represents the most significant absence. This spacecraft wasn't designed for pretty pictures. It was built to detect and analyze atmospheric gases at parts per trillion sensitivity. Its NOMAD and ACS instruments can identify trace molecules that other equipment would miss entirely, measuring isotopic ratios and chemical compositions with extraordinary precision. ESA launched this billion-dollar mission specifically to search for biosignatures in Mars's atmosphere to determine whether methane variations might indicate subsurface life. Those same instruments turned toward 3I Atlas's coma could have detected organic molecules at concentrations far below JWST's sensitivity threshold, could have searched for isotopic anomalies that might indicate artificial enrichment or exotic formation conditions, could have, in principle, found exactly the kind of biosignatures or technological markers that would answer the most profound questions about this visitor's nature. The Trace Gas Orbiter had the perfect geometry, the perfect instrumentation, the perfect opportunity, and its data remains locked away, unseen by the scientists who dedicated their careers to studying exactly these kinds of phenomena. The European Space Agency's silence is particularly noteworthy because ESA traditionally operates with different institutional culture than NASA. European space policy has generally favored rapid data release, international collaboration, public transparency. When ESA chooses to withhold observations, they typically provide clear explanations, calibration difficulties, instrument anomalies, proprietary periods for particularly sensitive measurements. But for 3I Atlas, there's been no explanation at all, just absence where presence was expected, silence where communication should flow naturally. This coordinated silence across multiple agencies and missions suggests decisions made at organizational levels far above individual research teams. It suggests policy rather than technical difficulties. It suggests that something about the 3I Atlas observations triggered protocols that override normal scientific transparency. And that realization is deeply unsettling because it implies that officials with access to the full data set have seen something they believe requires special handling, something significant enough to justify breaking with decades of open science tradition. Meanwhile, the amateur astronomy community has been filling the gap with their own observations. Citizen scientists with backyard telescopes, modest CCD cameras, and impressive dedication have been tracking 3I Atlas since its discovery. They share their data freely on forums and social media, collaborate across continents, pool their observations to extract every possible photon of information from this elusive visitor. In some ways, they're seeing what the official missions won't show us. And what they're seeing is strange. The brightness curve doesn't match predictions. As 3I Atlas approached perihelion, its closest point to the Sun in mid-November, standard cometary models predicted it should brighten dramatically to perhaps magnitude 7 or 8, potentially visible to the naked eye under dark skies. But the amateur observations cluster around magnitude 9 to 10, dimmer than expected, requiring optical aid to observe. Either the activity isn't increasing as it should near perihelion, or the nucleus is darker and larger than estimates suggested, absorbing rather than reflecting light in ways that don't match typical cometary surfaces. A comet that doesn't brighten appropriately near the Sun raises uncomfortable questions. Standard models assume that volatile sublimation accelerates steeply as solar radiation intensifies, creating more gas, more dust, more reflected light. But if the brightness curve flattens or deviates from predictions, something about our assumptions is wrong. Perhaps the surface is covered in a dark, non-volatile crust that insulates ice beneath, allowing only limited outgassing through cracks and vents. That happens sometimes with old comets that have made many passages through the inner solar system, their surfaces modified by repeated heating cycles. But 3I Atlas is making its first and only passage near our Sun, arriving pristine from interstellar space. It shouldn't have a weathered crust. It shouldn't show the kind of surface modification that comes from repeated thermal stress. Unless it isn't pristine, unless it's ancient in a different way, not weathered by solar passages, but by millions of years drifting through the interstellar medium, exposed to cosmic rays and micrometeorite bombardment, building up a processed mantle that's more complex than simple ice and dust. That would explain the unusual polarization, the strange chemistry, the unexpected activity patterns. Or perhaps the comet is managing its output actively, controlling its outgassing, releasing volatiles at rates determined by something other than passive solar heating. That's the explanation that refuses to stay buried no matter how many times we dismiss it with natural mechanisms. If you wanted to traverse interstellar space without losing too much mass to sublimation, you'd need to minimize unnecessary outgassing. If you were approaching a new star system, entering regions where temperatures and radiation intensities increase dramatically, you'd want control. You'd want to meter your volatile reserves carefully, ensuring you had enough for trajectory adjustments while preventing wasteful loss. Does that sound like paranoid speculation? Perhaps. But consider the alternative, that every anomaly is independent coincidence. The CO2 dominance is just unusual chemistry. The polarization is rare dust properties. The water activity is an unexpected natural phenomenon. The missing images are bureaucratic delays. The furloughs are unfortunate timing. The brightness curve is simply a comet behaving slightly differently than models predict, which happens occasionally. That's a lot of coincidences. That's a lot of independent anomalies all clustering around a single object in a compressed time frame. Occam's razor, that principle guiding scientific thought for centuries, tells us to prefer simpler explanations with fewer assumptions. But Occam's razor cuts both ways. Is it simpler to have a dozen unrelated anomalies, each requiring its own special explanation, or one underlying cause that accounts for multiple observations? If that cause is artificial object or technology, then yes, we're invoking something extraordinary. But extraordinary explanations become necessary when ordinary ones demand more coincidences than the extraordinary alternative. That's the uncomfortable position the astronomical community finds itself in with 3I Atlas. The remote viewing claims add another dimension to this puzzle, though discussing them makes many scientists uncomfortable. Remote viewing exists in that murky territory between documented Cold War research and fringe pseudoscience. The CIA and Defense Intelligence Agency spent millions investigating whether trained individuals could perceive distant locations using consciousness alone, programs like Stargate and Grill Flame that remained classified for decades. When declassified in 1995, the official conclusions were diplomatically vague. Some results exceeded chance expectations, but reliability remained too inconsistent for operational intelligence use. In August 2025, before the Mars closest approach, before the furloughs, before the public became broadly aware of 3I Atlas's significance, a group of remote viewers claimed they had targeted the object. Multiple viewers, working independently according to protocols designed to prevent contamination or leading, reported perceiving technology aboard the interstellar visitor. Not geological formations, not ice and rock, technology, structures, perhaps even active systems. The reports varied in specifics but converged on that central, impossible theme. This was not entirely natural. Now, we must be careful here. Remote viewing has never achieved scientific validation that satisfies mainstream research standards. Anecdotal successes might be chance, confirmation bias, cold reading, or any number of cognitive patterns the human brain naturally employs. The fact that multiple viewers reported similar impressions could reflect shared cultural expectations rather than genuine perception. When you ask people to remote view something called an interstellar object, their imaginations naturally drift toward science fiction tropes. Ancient probes, alien artifacts, the same stories we've been telling ourselves since the dawn of space-age speculation. But here's what gnaws at careful skepticism. The remote viewing reports emerged in August, before the scientific anomalies became widely known, before JWST published the CO2 dominance findings, before the polarization papers described unprecedented characteristics, before the unusual water activity patterns were documented. The viewers reported technology in August. The scientific impossibilities emerged in September and October. If this was simply imagination or cultural contamination, why did objective instrumental measurements later corroborate the idea that something about 3I Atlas was profoundly unusual? Correlation isn't causation. That's the first wall protecting reason from wild speculation. But correlation can be suggestive. It can point toward questions worth asking, even if those questions make us uncomfortable. The uncomfortable question is this: if remote viewers detected something in August that scientific instruments later confirmed in their own language, anomalous, unprecedented, impossible, does that lend any credibility to the consciousness-based claims? Or is it pure coincidence, the universe playing tricks on our pattern-seeking minds? Let's examine what we actually know, stripped of speculation and paranormal overlay. We know 3I Atlas is compositionally bizarre, with CO2 to water ratios that challenge our models of comet formation. We know its dust scatters light in ways never before recorded, suggesting particle properties fundamentally different from solar system norms. We know it produces water far from the sun with unusually widespread surface activity. We know it was photographed from Mars by Perseverance, but higher resolution images from more capable platforms remain unreleased. We know NASA furloughed thousands of employees on the day of optimal observation. These are facts documented in papers and official announcements. What we suspect, the missing images might indicate something unexpected discovered but not yet disclosed. The trajectory might show deviations suggesting non-gravitational forces more regular than natural outgassing typically produces. The object might possess properties that don't fit cleanly into natural categories. Someone might be withholding information for reasons they consider justified but haven't explained. These are possibilities, inferences drawn from gaps in what we know, interpretations of silence that begs for explanation but receives none. The distance between facts and suspicions is where truth hides in shadows. Sometimes that distance contains only mundane explanations, bureaucratic delays, technical failures, budget cuts whose timing is unfortunate but meaningless. Sometimes it contains something more significant. The art of understanding requires holding both possibilities simultaneously, accepting uncertainty rather than rushing toward premature conclusions that comfort but mislead. And that's genuinely difficult. Human psychology craves closure, answers, certainty. We want to know whether Three-Eye Atlas is natural or artificial, whether the silence is conspiracy or coincidence, whether we're witnessing history or misreading random patterns. But the universe rarely cooperates with our desire for simple narratives. Let's talk about what makes an interstellar object interstellar. It's not just about origin, though that matters enormously. It's about velocity, about carrying speed that exceeds what our sun's gravity can capture. Everything in our solar system orbits at speeds determined by distance and gravitational physics. Earth travels about 30 kilometers per second. Objects in the distant Kuiper Belt drift at 5 kilometers per second or less. But they're all bound, trapped in elliptical paths that cycle endlessly around our star. An interstellar object arrives with excess velocity, speed inherited from its origin system, and the long fall through the galaxy's gravitational landscape. When Oumuamua passed through in 2017, it moved at roughly 26 kilometers per second relative to the Sun. That speed, combined with its trajectory, meant it would escape our system entirely, never to return. No amount of solar gravity could bend its path into a closed orbit. It came, it passed, it left. A true visitor from beyond. Three-Eye Atlas carries similar excess velocity. Calculations show it will leave the solar system at approximately 35 kilometers per second, relative to the Sun. That's escape velocity at this distance, plus additional speed brought from interstellar space. You can work backward from exit velocity to infer origin, calculate which star systems might have been home, trace probable paths through millions of years of galactic motion. The mathematics is complex, accounting for stellar movements, gravitational perturbations from nearby stars, the uncertain duration of the journey. But they provide possibilities, candidate systems this visitor might have once orbited. The leading candidates include several red dwarf stars within a few hundred light-years of our solar system. Red dwarfs are the galaxy's most common stellar type, small, cool, long-lived. They're also notoriously violent in their youth, prone to massive flares that blast nearby space with radiation and charged particles. A comet forming in a red dwarf system might experience radiation environments vastly different from our Sun's relatively gentle output. High-energy particles can process ices, break molecular bonds, reform them in unexpected configurations. Perhaps that explains the CO2 dominance, the unusual chemistry, the strange polarization properties. But here's the frustrating reality. We cannot know origin with certainty. Trajectory calculations backward through time become increasingly uncertain as errors propagate and accumulate. After 1,000,000 years of drift through the galaxy, even tiny measurement uncertainties in current position and velocity expand into vast regions of possibility space. We can narrow the list to candidate stellar neighborhoods, but we cannot point at a specific star and declare with confidence, there, that's home, unless we find something more definitive, unless we discover a signature that screams origin in ways trajectory calculations cannot. What would such a signature look like? In natural objects, isotopic ratios. The proportions of different atomic isotopes reveal formation conditions, the temperature and pressure and radiation environment where molecules first froze together. Every stellar system has a unique isotopic fingerprint, subtle variations in deuterium to hydrogen ratios, in carbon-13 versus carbon-12, in oxygen isotopes. If we could analyze 3I Atlas's composition in molecular detail, compare isotopic signatures to models of different stellar formation environments, we might pinpoint origin with real confidence. But if 3I Atlas isn't entirely natural, if it carries artificial components or technological elements, the signature might be entirely different. Geometric structures too regular for geological processes. Electromagnetic emissions at frequencies natural objects don't produce. Chemical compounds that require synthesis rather than natural cosmic chemistry. Isotopic ratios that are too pure, too refined, showing evidence of enrichment or separation processes that demand technology. This is why high-resolution imaging matters so profoundly. This is why the missing high-rise data cuts so deeply into our understanding. A detailed photograph might answer questions that spectroscopy alone cannot resolve. The Hubble Space Telescope observed 3I Atlas in August, before the Mars closest approach. Hubble operates in visible and ultraviolet wavelengths with resolution sufficient to reveal nuclear structure in comets, to show irregular shapes and brightness variations that indicate rotation or surface features. Those observations remain unreleased, which is less unusual than the Mars data. Hubble observations typically go through proprietary periods where requesting scientists have exclusive access before public release. That's standard procedure, protecting the researchers who proposed and planned the observations. But the timing, once again, raises eyebrows, the most anomalous interstellar object ever detected, and we're still waiting for images. There's a spacecraft in the outer solar system that might become relevant, New Horizons. After its spectacular Pluto flyby in 2015 and encounter with Kuiper Belt object Arrokoth in 2019, New Horizons continues outward, exploring the boundary between solar and interstellar space. It's not positioned to observe 3I Atlas directly. The geometry doesn't align. Distances are too vast. But New Horizons carries instruments designed to study the interstellar medium, that thin soup of gas and dust between stars. If 3I Atlas is shedding material with unusual isotopic or chemical signatures, New Horizons might detect traces long after the comet has passed. That's admittedly a long shot. Space is incomprehensibly vast, and odds of New Horizons intersecting 3I Atlas's trail are vanishingly small. But NASA has used New Horizons for opportunistic observations before, pointing cameras at distant objects when nothing else demands attention. The spacecraft operates on minimal budget now, with infrequent ground contact to conserve funds. But it's still functional, still capable, still sending back data from the edge of everything we've explored. If there's anything unusual in the wake of this visitor, New Horizons might be our only chance to sample it directly. The asteroid belt between Mars and Jupiter presents another consideration. 3I Atlas's trajectory carried it through the belt during August and September. If the object shed material, if fragments broke off either naturally through thermal stress or deliberately through some kind of deployment, those pieces might remain in solar orbit. Small chunks of interstellar matter too tiny to detect as independent objects, but potentially recoverable by future missions. The asteroid belt becomes a repository, a museum of Three-Eye Atlas's passage, waiting for someone with technology and determination to go looking. Japan's Hayabusa 2 spacecraft proved we can rendezvous with small bodies, collect samples, return them to Earth for detailed laboratory analysis. NASA's OSIRIS-REx accomplished the same feat with asteroid Bennu, bringing back pristine material that will be studied for generations. The technology exists for sample return missions to challenging targets. The question is whether anyone has the foresight and resources to plan such missions for interstellar fragments that might be scattered along Three-Eye Atlas's path, or whether they already have, quietly, without public announcement or media attention. There are military spacecraft we don't hear about, payloads launched without detailed mission descriptions, classified assets that might be far more capable than public programs suggest. When something unprecedented happens, when an anomalous interstellar object passes through, displaying characteristics that challenge natural explanations, it would be naive to assume that only civilian scientific institutions are paying attention. Military and intelligence organizations that spend billions on space surveillance, that track every piece of debris in Earth orbit, that monitor potential threats from above. They've certainly noticed Three-Eye Atlas, and they might have capabilities to investigate that civilian programs lack. That speculation ventures into territory difficult to verify or disprove. But it's worth considering. If you're a nation with advanced space capabilities and you detect something that might represent technology from beyond our solar system, would you announce it immediately to the world? Or would you attempt to gather intelligence first, determine capabilities and intentions, assess whether this represents opportunity or threat? The gap between what civilian scientists know and what classified programs might have discovered could be substantial. And that gap would explain the peculiar silence, the coordinated withholding of data, the sense that official channels are speaking carefully around something they're not ready to disclose. The concept of panspermia, life spreading between worlds on comets and asteroids, has existed in scientific discourse for over a century. The mathematics works elegantly. Microorganisms can survive space travel when protected by even thin layers of rock or ice. Impact events regularly launch material from the planetary surfaces with enough velocity to escape gravity. Over geological timescales, solar systems exchange material, potentially exchanging life itself. Mars and Earth likely share rock, fragments blasted into space by asteroid impacts, drifting through orbits that eventually intersect with the other world. Life, if it exists on Mars, might be related to Earth life. We might be distant cousins, separated by a meteor's throw. Now extend that concept to the galaxy. Supernovae explode with violence that can strip away outer planets entirely, hurl comets into interstellar void at tremendous velocities. Those comets carry whatever biology existed in their home system, frozen in time, dormant, but potentially viable for millions of years as they drift between stars. Eventually, some fraction, tiny but non-zero, encounter new solar systems, get captured by gravity, impact planets, deliver their microscopic cargo. Galactic panspermia. Life as cosmic seed, spreading from star to star, not through deliberate action, but through patient time and random chance, If 3I Atlas originated from a system where life evolved, if it formed from the same primordial material that coalesced into that system's planets, it might carry biosignatures, organic molecules more complex than simple hydrocarbons, amino acids, perhaps in ratios suggesting biological origin rather than random chemical synthesis. The line between complex organics and evidence of life is frustratingly blurry. Meteorites contain amino acids produced through ordinary cosmic chemistry, nothing living required. But certain patterns, homochirality, where organic molecules prefer one mirror image form over another, don't occur naturally at high concentrations. That requires biology, the templating effect of self-replicating molecules. Has anyone searched for biosignatures in 3I Atlas? The spectroscopic observations from JWST and ground-based telescopes focused on volatiles, carbon dioxide, water, carbon monoxide, simple molecules that sublimate readily and dominate the coma. Detecting complex organics requires different techniques, different wavelengths, longer integration times to catch faint spectral features among brighter signals. It's possible such observations are planned or underway, results not yet published. It's also possible no one thought to look, assuming an interstellar comet would be as sterile as solar system comets appear. Organic chemistry, yes, but nothing approaching biology. If someone did look and found something, found biosignatures that couldn't be explained by abiotic processes, found chemical patterns that screamed life rather than whispered possibility, that would certainly qualify as information worth withholding until absolutely confirmed. That would be discovery of the century, perhaps the millennium. First, confirmed evidence of biology beyond Earth, arriving not from radio signals or atmospheric spectroscopy of distant exoplanets, but literally dropping into our cosmic backyard. Such a discovery would demand extraordinary care in verification before announcement. Peer review so rigorous it borders on paranoid, multiple independent confirmations before speaking words that cannot be unspoken. The ExoMars Trace Gas Orbiter deserves special attention in this biosignature context. Unlike Mars Reconnaissance Orbiter or Mars Express, which are primarily imaging spacecraft, the Trace Gas Orbiter was designed specifically to detect and analyze atmospheric gases at parts per trillion sensitivity. Its NOMAD and ACS instruments can identify methane, water vapor, ozone, and far more exotic molecules with extraordinary precision. ESA built this billion-dollar mission to search for biosignatures in Martian atmosphere, to determine whether seasonal methane variations might indicate subsurface biological activity. Those same instruments, turned skyward toward 3I Atlas's coma, could analyze composition with detailed orders of magnitude beyond JWST's capabilities, could detect organic molecules at concentrations that Earth-based telescopes would miss entirely, could search for isotopic anomalies, for ratios that don't match natural cosmic chemistry, for patterns that might indicate biological processing or technological enrichment, could, in principle, find exactly the kind of signatures that would answer the most profound questions about this visitor's nature and origin. If such observations were conducted, and the geometry suggests they should have been, the opportunity was geometrically perfect, then the Trace Gas Orbiter might possess the most sensitive chemical analysis of an interstellar object ever performed by human instruments. That data, like the high-rise images, remains unreleased. ESA's public data archives show nothing about 3I Atlas observations from any of their Mars spacecraft. The silence is total, coordinated across multiple missions and instruments. Individual missions might delay data release for technical or scientific reasons specific to their operations. But 3 missions simultaneously remaining silent. That suggests policy decisions made at organizational levels that transcend individual spacecraft management. European space policy traditionally favors openness, rapid data release, international scientific collaboration. ESA's institutional culture differs from NASA's in many ways, shaped by different funding structures and political contexts, but both share commitment to transparency, born from public funding and scientific norms. When ESA chooses to withhold data, it's usually for clearly stated reasons: calibration difficulties, instrument anomalies, competitive proprietary periods for particularly sensitive observations. But none of those standard explanations have been offered for 3I Atlas observations. There's just absence where presence was expected, silence where communication should flow naturally according to decades of established practice. October turned to November as we speak quietly through this long night. The comet approached perihelion, that moment of closest solar encounter when solar heating peaks and activity should reach maximum intensity. Ground-based telescopes, no longer staring into the sun's overwhelming glare, regained clear views of 3I Atlas. Amateur astronomers with backyard equipment captured images, tracked the comet's evolution, measured brightness and tail development. These citizen scientists, unburdened by institutional constraints or classification concerns, share their data freely, post images to forums and social media, collaborate across continents in real-time analysis. In some ways, amateurs are seeing things official missions haven't shown us, or won't show us, or can't show us for reasons that remain frustratingly unstated. The amateur observations reveal something interesting. 3I Atlas is brightening, but not as dramatically as models predicted. For a comet at 0.75 astronomical units from the Sun, with activity levels detected at greater distances, standard brightness equations suggest it should reach magnitude 7 or 8, potentially visible to naked eye under dark skies. But reports cluster around magnitude 9 to 10, dimmer than expected, requiring binoculars or small telescopes to observe. 2 explanations present themselves. Either activity isn't ramping up as it should near perihelion, suggesting something about composition or structure suppresses expected volatility, or the comet is larger and darker than estimates suggested, reflecting less sunlight than anticipated, absorbing rather than scattering the photons that strike its surface. Both explanations carry implications. Suppressed activity near perihelion is unusual for comets making first solar approach, arriving pristine with maximum volatile inventory. Large, dark surfaces suggest either ancient processing or intentional design, choosing materials for properties other than high reflectivity. The amateur community has also been tracking rotation, attempting to measure how fast 3I Atlas spins from periodic brightness variations as different surface areas face toward Earth. The data quality makes firm conclusions difficult, but preliminary analyses suggest rotation period around several hours, faster than many solar system comets, but not impossibly so. What's more interesting is the stability of that rotation. Natural objects tumbling through space for millions of years typically develop chaotic rotation patterns, influenced by gravitational encounters and outgassing torques. But 3I Atlas seems to rotate smoothly, regularly, as if maintaining orientation through some stabilization mechanism we cannot identify. Distributed amateur analysis represents a hedge against institutional silence. If official sources won't provide answers, if the most capable instruments remain mute, the amateur community extracts what it can from publicly available data. It's not as good as having high-rise images or trace gas orbiter spectra, but it's something. It's ground truth against which institutional claims can be evaluated, independent verification that prevents complete narrative control. And in this case, what the amateur community sees is an object that doesn't quite fit, that demonstrates properties no one predicted, that demands explanations beyond comfortable categories we've built for cosmic phenomena. The physics constrains possibilities even if it doesn't uniquely determine answers. An object arriving from interstellar space, moving on hyperbolic trajectory, must have formed either in another star system or in dark spaces between stars. Formation in interstellar space is theoretically possible. There are molecular clouds where gas density reaches levels sufficient for ice accumulation on dust grains, building larger aggregates over millions of years. But those objects tend to be small, dark, compositionally similar to cloud material, dominated by water ice and simple carbon compounds. 3I Atlas's CO2 dominance and unusual dust properties don't fit that origin scenario well. So we return to formation in a planetary system around some distant star we may never identify with certainty. The question becomes, what kind of planetary system produces comets so profoundly different from our own? Our solar system's comets, both short-period Jupiter family and long-period Oort cloud objects, show fairly consistent compositions because they formed from the same primordial nebula, the same disk of gas and dust that collapsed to birth sun and planets. Variations exist, reflecting different formation locations and temperatures, but overall, patterns remain recognizable. Their family, sharing genetic markers traceable to common ancestry. 3I Atlas comes from different family, formed under different conditions. Perhaps a star system richer in carbon relative to oxygen than our Sun, where CO2 and carbon compounds dominate over water throughout planet-forming regions. Perhaps a system where stellar radiation from more active young star photoprocessed protoplanetary disk ices, breaking down water preferentially, leaving CO2 enhanced in residual material. Perhaps a system that experienced unusual dynamical evolution, where giant planets migrated differently. Heated disk asymmetrically created compositional gradients steeper than what our system shows. Each scenario can be modeled, tested against what we understand about planetary formation and stellar evolution. Each produces predictions about what else we should see when observing objects from similar origins. If interstellar visitors are common, if 3I Atlas represents typical example from some population of extrasolar comets, we should expect future visitors to show similar properties. More CO2 dominance, more unusual polarization, more anomalies challenging solar system-derived intuitions. Establishing that pattern would be enormously valuable scientifically, confirming that diversity of planetary systems we see in exoplanet observations extends to small body populations as well. But if 3I Atlas is unique, if future interstellar visitors don't share its properties, we're left with sample of one that defies broader context, an outlier not just in our experience, but potentially in galaxies' population of natural objects. And outliers demand special attention, demand explanations that might not apply to general cases. That's when artificial hypothesis gains traction, not from one or two anomalies, but from sustained pattern of uniqueness, from objects' refusal to fit any natural category cleanly without invoking multiple special conditions that stretch coincidence beyond breaking. We're in waiting game now, watching as 3i Atlas rounds Sun and begins outbound journey. Every day brings new observations, new data points, new opportunities to constrain properties and test hypotheses. The JUICE mission, Jupiter Icy Moons Explorer, intends to observe 3i Atlas during November 2025. JUICE launched in April 2023 on an 8-year journey to Jupiter's ocean-bearing moons, Ganymede, Callisto, Europa. While still in inner solar system performing gravitational assists, it's scheduled to turn instruments toward this interstellar visitor. JUICE carries sophisticated equipment, Janus camera system, MAGIS spectrometer for infrared imaging, UVS ultraviolet spectrograph. These aren't instruments designed for cometary observation. They're built to study Jupiter's magnetosphere and icy moon surface compositions, but they're capable of opportunistic science. Pointed at 3i Atlas for hours of integration time, they should return data far superior to what Earth-based telescopes can achieve when comet sits near Sun in our sky. By November, the object will have passed perihelion, swung around Sun, begun exit trajectory. It will be more active, potentially sporting dramatic tail as solar heating peaks and volatiles stream away in visible splendor. The announcement of JUICE observations came with carefully worded enthusiasm from ESA scientists. An opportunity, bonus science target, chance to study interstellar visitor during peak activity phase. But it also serves another function, second chance. If Mars observations failed, if data remains unreleased for whatever reasons, JUICE provides another opportunity to capture clear images and spectra before 3i Atlas leaves forever. Another chance to answer questions that October's silence left hanging uncomfortably in institutional void. Unless JUICE observations also experience difficulties, unless its data also remains unreleased or heavily delayed. At some point, pattern of withholding becomes impossible to dismiss as coincidence or mundane failure. At some point, you must ask, what are they seeing that we're not being shown? What discovery could be significant enough to justify this coordinated institutional silence? The possibilities range from mundane to extraordinary, from embarrassing technical failures to profound discoveries that challenge fundamental assumptions about our cosmic situation. The remote viewing claims gain strange credibility in this context, not because remote viewing has been validated, it hasn't, not to scientific standards, but because prediction of technology came before scientific anomalies and before observation difficulties. If someone wanted to prepare public consciousness to prime populations for shocking revelation without triggering immediate panic, they might do it exactly this way. Leak conclusion through unconventional channels that don't carry institutional weight. Let conspiracy theorists and fringe communities run with idea. Then when official announcement comes, if it comes, public has been softened, pre-exposed to concept, less likely to react chaotically. That's psychological operations theory, information warfare doctrine. It's how governments have historically prepared populations for difficult truths, gradually, through indirect channels, creating familiarity before confirmation. But it's also pattern that conspiracy theorists see everywhere, whether it exists or not. Human mind craves narrative coherence. We connect dots into pictures even when dots are random scatter. So we must remain disciplined, must separate what we know from what we suspect, what we can prove from what merely resonates with pattern-seeking instincts that evolution gifted us for survival in very different contexts than interstellar visitor analysis. What we know with certainty. 3I Atlas is compositionally anomalous, with CO2 to water ratio exceeding any previously observed comet by extraordinary margins. Its dust scatters light with unprecedented polarization, characteristics suggesting particle properties fundamentally different from solar system norms. It produces water far from sun across unusually large active surface area. It was photographed from Mars by Perseverance rover, but higher resolution observations from orbital platforms remain unreleased weeks later. NASA furloughed thousands of employees on day of closest approach. Remote viewers reported technology before scientific anomalies became public knowledge. These are documented facts, verifiable through published papers, official announcements, and image archives. What we suspect but cannot prove, missing Mars Reconnaissance Orbiter images, might indicate something unexpected discovered but not disclosed. Trajectory might show deviations, suggesting non-gravitational forces more regular than natural outgassing typically produces. Object might possess properties or behaviors that don't fit natural comet models developed from solar system examples. Someone might be withholding information for reasons they consider justified, but haven't explained publicly. These are possibilities, inferences drawn from gaps in expected data, from silences that beg explanation but receive none from official channels. The distance between facts and suspicions is where truth hides in shadows, waiting for patient observers who can distinguish signal from noise, pattern from pareidolia. Sometimes that distance contains only mundane explanations, bureaucratic delays, technical failures, budget cuts whose timing is unfortunate but meaningless coincidence. Sometimes it contains something more significant, discoveries that challenged paradigms, observations that demand careful verification before announcement, because their implications touch every human who looks up at night sky, wondering about our place in vast cosmic arena. The art of understanding requires holding both possibilities simultaneously, without collapsing prematurely into comfortable certainty that relieves tension but might blind us to truth. That's genuinely difficult. Human psychology evolved for rapid decision-making in contexts where hesitation meant death, where pattern recognition mattered more than perfect accuracy, where false positives were safer than false negatives. We want answers. We crave closure. We need to know whether 3I Atlas is natural or artificial, whether silence is conspiracy or coincidence, whether we're witnessing history or misreading random cosmic events through lens of our own hopes and fears. But universe rarely cooperates with our psychological needs for simple narratives. Let's talk about what happens next, about opportunities still ahead for understanding this enigmatic visitor. Ground-based telescopes continue tracking 3I Atlas as it moves outbound from perihelion, crossing back through inner solar system toward distant reaches where it will eventually fade from even our most sensitive instruments. Each night brings new photometry, new spectroscopy, new chances to detect changes in activity or composition as solar heating decreases and object begins its long return to interstellar cold. The Hubble Space Telescope observations, whenever released, should provide crucial information about nuclear structure and rotation. Hubble's resolution in visible wavelengths can reveal shape, distinguish between spherical nucleus and elongated body, show whether surface brightness varies in ways suggesting heterogeneous composition or geometric features. Those observations occurred in August when object was still approaching Sun, activity ramping up but not yet at peak. The data exists somewhere in archives, either being carefully analyzed before publication or deliberately withheld for reasons unstated. Additional JWST observations are planned for post-perihelion period, when comet begins outbound journey, and scientists can compare composition measurements at different solar distances. How does CO2 to water ratio change as object moves away from Sun and temperatures decrease? Does activity shut down uniformly across surface, or show regional variations suggesting heterogeneous internal structure? These measurements will help constrain formation conditions, provide clues about whether extreme CO2 dominance is intrinsic property of nucleus or artifact of observation timing and solar heating patterns. Ultraviolet spectroscopy from both space-based and high-altitude balloon instruments can detect hydroxyl emission and other photodissociation products with sensitivity complementing infrared observations. UV reveals different aspects of coma chemistry, particularly products of solar radiation breaking apart molecules. Comparing UV and infrared data helps reconstruct a complete picture of volatile composition, filling gaps that individual instruments leave. But UV observations require clear sight lines above Earth's atmosphere, which absorbs most ultraviolet light. That means space telescopes or specialized balloon platforms flying at extreme altitudes where atmosphere thins to near vacuum. Continued polarimetric monitoring as 3i Atlas moves through different phase angles will help determine whether unprecedented negative polarization was measurement artifact or genuine property requiring exotic explanations. Polarization depends on observation geometry, the angle between Sun, object, and observer, so measurements at multiple phase angles provide constraints on particle properties that single observations cannot. If polarization characteristics remain extreme across various geometries, that strengthens case for genuinely unusual dust composition or structure in coma. Radio observations continue searching for any electromagnetic emissions beyond expected background noise. The Breakthrough Listen project, funded by Yuri Milner's Foundation and representing most comprehensive SETI effort ever undertaken, has been monitoring 3i Atlas for radio signals that might indicate technology. When Oumuamua appeared in 2017, Breakthrough Listen pointed Green Bank telescope at it for hours, searching frequency ranges where artificial transmissions might occur. They found nothing, no narrow-band signals, no modulated carriers, no evidence of technology in electromagnetic spectrum they surveyed. They're conducting similar observations of 3i Atlas, using multiple facilities to cover different frequency ranges and improve sensitivity. If object carries active technology, communication systems, propulsion, power generation, it might leak electromagnetic radiation, detectable across interplanetary distances. The inverse square law works against detection. Even powerful transmissions weaken to whispers across millions of kilometers. But we're looking systematically with instruments capable of detecting cell phone strength signals from Mars orbit. If there's anything broadcasting, we should find it, assuming it broadcasts in frequencies and modulations we're monitoring, unless technology is quiet by design, unless whatever intelligence might have built this object understood importance of stealth, of not announcing presence to every civilization within detection range. We assume advanced technology would be loud, radiating waste heat and electromagnetic noise as inevitable byproducts of operation. But that assumption stems from our own technological adolescence, from civilization that's only recently learned to generate power at scale, and still does so inefficiently, spilling waste into every available channel. Mature technology, refined over thousands or millions of years of development, might be extraordinarily efficient, minimizing waste, recycling every photon and joule, presenting almost no signature to external observers searching for conventional markers. That's the dark forest hypothesis applied at solar system scale. The idea that galaxy might be filled with civilizations remaining deliberately silent, hiding from each other out of game-theoretic caution, assuming any unknown civilization represents potential threat best avoided. If you're sending probes to explore other stellar systems, you might design them for maximum stealth, to observe without being observed, to gather data without revealing presence or capabilities. CO2-dominated coma provides excellent camouflage for such probe. Looks like natural comet, behaves mostly like one, draws no special attention unless examined very carefully with very sensitive instruments. But then, why be visible at all? Why allow detection if stealth is goal? Perhaps because perfect stealth is impossible at these scales, or energetically expensive beyond mission parameters, or because mission doesn't require hiding from civilizations at our technological level. Perhaps probe is only stealthy to peer competitors, to other advanced civilizations that might pose actual threats, while remaining visible to younger species who lack capability to meaningfully interfere. We can photograph it, analyze spectra, write papers about anomalous properties, but we cannot reach it, cannot intercept it, cannot affect its mission in any substantial way. From probe's perspective, we're irrelevant. Interesting, perhaps, data points to be logged and transmitted homeward, but not actors requiring countermeasures or evasion. That's humbling thought, isn't it? That we might be witnessing something extraordinary, something proving we're not alone in universe, and from phenomenon's perspective, we simply don't matter enough to hide from. But perhaps humility is appropriate here. We've only been broadcasting radio signals for a century, only been spacefaring for 60 years, only detected planets around other stars for 3 decades. On cosmic timescales, we emerged from caves heartbeat ago. If galaxy hosts civilizations millions of years old, civilizations that solved problems we haven't conceived, their attitude toward us might be analogous to our attitude toward ants. Awareness? Yes. Concern? No. Intervention only if we happen to be in their path. The Fermi paradox asks why, if intelligent life is common in galaxy, we see no evidence of it. No radio signals from stars, no megastructures dimming distant suns, no von Neumann probes replicating across galaxy until every solar system hosts their descendants. The silence seems profound, suggesting either we're alone, or intelligence is vanishingly rare, or something prevents civilizations from expanding and broadcasting presence. But perhaps paradox rests on flawed assumption, that we would recognize artificial when we see it, that our instruments and intuitions are adequate to distinguish technology from nature at first glance? What if galaxy is full of artifacts and we've been looking at them for centuries without recognition? What if some asteroids in our own solar system aren't entirely natural? What if some comets are probes in hibernation, waiting for triggers we don't understand? What if Oumuamua was first that we almost recognized, its behavior strange enough to spark debate, and 3I Atlas is second, its anomalies sharp enough to demand attention even from skeptics? Sample size grows slowly. Pattern, if there is one, begins emerging from noise. And maybe, just maybe, people with most sensitive instruments, those who can see details invisible to public observatories, have recognized something forcing them to silence while they decide how to respond. That's optimistic interpretation of silence, that it's thoughtful, deliberate, responsible. That powers making decisions are carefully considering implications, consulting experts across disciplines, preparing humanity for revelation that will fundamentally alter our self-understanding. Better to take time to be certain, to plan announcement carefully, than to rush forward with half-formed conclusions that might be wrong and cause unnecessary disruption. Better to verify through multiple, independent channels before speaking words that cannot be unspoken, claims that cannot be retracted without permanent damage to institutional credibility. But there's darker interpretation. That silence is about control, about managing information deemed too dangerous or destabilizing for public knowledge. That governments and space agencies have decided, unilaterally, that certain discoveries should remain classified because release might undermine social order, trigger religious crises, cause economic panic, or reveal strategic vulnerabilities. In this interpretation, we're not being protected by thoughtful stewardship, but controlled by paternalistic institutions that don't trust populations with truth, that assume we cannot handle paradigm-shifting information without descending into chaos. Which interpretation is correct? We cannot know from outside information barrier, that's nature of secrets, from perspective of those excluded, both benign and malicious motives can explain same observable silence. All we can do is watch for leaks, for cracks in narrative, for inconsistencies revealing more than intended. The Perseverance images represent one such crack. They shouldn't exist in public archives if someone wanted total information control. Their presence suggests either incomplete coordination between NASA's public data release pipeline and whatever policy governs 3I Atlas information, or deliberate choice to allow some information out while withholding highest quality observations. Simeon Schmaus, the astrophotographer who stacked those Perseverance frames, became briefly famous in spaces where people follow these developments closely. Forums dedicated to amateur astronomy, communities tracking solar system interlopers, channels analyzing UAPs and potential alien technology. His name circulated as someone who saw what institutions weren't showing, who applied skill and patience to reveal truth hiding in publicly available data. Whether that fame pleases or troubles him, we cannot say. But his work illustrates something important. In age of open data policies and distributed analysis tools, complete information control is nearly impossible. Someone with time, skill, and motivation can extract signals from noise, can find needles in haystacks of raw data, can shine light into corners that someone else wanted dark. Every spacecraft operated by NASA and ESA releases thousands of raw images monthly, most never analyzed by professional scientists, archived for potential future use, but primarily sitting untouched in vast digital libraries. Citizen scientists comb through those archives looking for anything interesting, anything anomalous, anything telling stories official mission narratives don't emphasize. They've found atmospheric phenomena on Mars that researchers missed. They've tracked storms on Jupiter that went unnoticed. They've identified surface features on asteroids and comets from data that would otherwise languish unused. And occasionally, they find things raising uncomfortable questions. Imaging artifacts that look almost too regular to be natural. Atmospheric anomalies seeming to move with purpose. Spectral signatures in archived data not matching any known mineral or compound. Most turn out to be misunderstandings, compression artifacts, noise patterns misinterpreted, natural phenomena outside finders' expertise. But some remain unexplained even after expert scrutiny. Some sit in liminal space between probably natural and possibly significant, waiting for additional data or better theoretical models to resolve them into categories we understand. 3I Atlas has generated cottage industry of such analysis. Every image released, every spectrum published gets downloaded, enhanced, reprocessed, viewed from different angles, cross-referenced against predictions and models. People measure comets' rotation period from brightness variations, though data quality makes firm conclusions difficult. People track coma's evolution, watching for changes in structure or activity, revealing something about hidden nucleus beneath. People build detailed 3D trajectory visualizations, plotting where 3I Atlas has been and where it's going with precision, rivaling institutional ephemerides. All this distributed effort represents hedge against institutional failure or institutional silence. If official sources won't provide answers, if most capable instruments remain mute, amateur community extracts what it can from whatever data exists in public domain. It's not as good as having high-rise images or trace gas orbiter spectra, but it's something. It's ground truth against which institutional claims can be evaluated, independent verification preventing complete narrative control. And in this case, what amateur community sees is object that doesn't quite fit. That demonstrates properties no one expected. That demands explanation beyond comfortable boxes we've built for categorizing cosmic phenomena. The distributed analysis has revealed subtle features in 3I Atlas's coma that raise additional questions. When multiple amateur observations are stacked and carefully processed, the coma shows asymmetries that don't match typical dust distribution patterns. Natural comets develop asymmetric comas due to rotation and solar radiation pressure, yes, but patterns follow predictable models. 3I Atlas shows brightness variations suggesting either unusual rotation axis orientation or localized outgassing from specific surface regions in ways that seem almost deliberate, as if venting from discrete ports rather than sublimating chaotically across entire illuminated hemisphere. The tail structure also shows peculiarities when examined in different wavelengths. Most cometary tails separate into two distinct components: dust tail, curved by solar radiation pressure and following object's orbital path, and ion tail, straight and pointing away from sun, shaped by solar wind interaction with ionized gas. But 3I Atlas displays what some observers describe as triple tail structure, with additional faint component that doesn't align with either expected pattern. Could be observational artifact, overlapping background stars creating false impression. Could be unusual dust grain size distribution creating optical effects. Or it could be something we don't have natural explanation for yet. The European Space Agency's planned observations from ground-based facilities continue through November and December as 3i Atlas becomes more favorably positioned for European longitude observations. ESA operates several world-class telescopes in partnership with member nations, instruments that can conduct detailed spectroscopy and photometry unavailable to most amateur observers. Whether those observations will be publicly released in timely fashion or subject to same delays affecting Mars spacecraft, data remains to be seen. But the observations are happening, data is being collected, and eventually, whether through official channels or leaks, information will emerge providing clearer picture of this enigmatic visitor. The scientific process, for all its careful methodology and peer review, cannot completely suppress information forever in modern connected world. Too many people have access. Too many independent observations occur. Too many amateur scientists possess skills approaching professional levels. If 3i Atlas truly represents something extraordinary, first contact with alien technology, evidence of life beyond Earth, natural phenomena requiring new physics, the truth will eventually emerge through accumulated observations no single institution can control. The question is timing. Will disclosure be managed carefully by official sources, or will it leak chaotically through fragmented channels, creating confusion and potentially panic? History provides uncomfortable lessons about both approaches. Managed disclosure risks being too slow, too cautious, breeding conspiracy theories and mistrust that poison public discourse. Information leaks risk being fragmentary, misinterpreted, triggering premature reactions based on incomplete understanding. Perhaps there's no perfect path, no ideal way to handle paradigm-shifting discovery that challenges fundamental assumptions millions of people hold about humanity's place in cosmos. Perhaps we must accept that transition from cosmic loneliness to cosmic companionship, if that's what we're witnessing, will be messy, contentious, marked by debate and uncertainty, rather than clean revelation. What we do know is that 3i Atlas will not wait for us to resolve our institutional difficulties or philosophical debates. It follows trajectory determined by physics, by momentum and gravity, by forces that care nothing for human readiness or comfort. By early 2026, it will cross beyond Jupiter's orbit, fading from view even for most powerful telescopes, returning to interstellar darkness from which it emerged. We have months at most to study it, to gather every possible scrap of data, to answer questions that keep astronomers awake through long nights and fill forums with speculation. The clock runs whether we're ready or not. The opportunity is finite, governed by orbital mechanics that cannot be negotiated or delayed, and choices made now about observation priorities, data sharing, transparency versus caution will determine what we learn and what we miss, what we understand and what remains forever mysterious because we failed to look while we had chance. That pressure, knowing window is closing, knowing this visitor will never return, adds urgency to every observation, every analysis, every debate about what should be public and what should remain classified. So rest now if you can. Let these questions settle into your mind, where they'll work quietly while you sleep, making connections, suggesting patterns, preparing insights that will surface when you wake. The universe is patient in ways we cannot match. Stars burn for billions of years, indifferent to human timescales, to our urgent need for answers within single lifetimes. 3i Atlas continues its journey whether we watch or not, whether we understand or remain confused, whether we're ready for implications or still clinging to comfortable certainties that its existence challenges. The dawn is coming. You can feel it in the way darkness begins softening at edges, the way silence prepares to yield to day's first sounds. We've traveled far together through this long night, following trail of interstellar visitor that refuses to fit our expectations, that demands more questions than it answers. The mystery remains unsolved, silences unexplained, anomalies unresolved. Perhaps that's appropriate. Perhaps some mysteries need time to ripen, data to accumulate, understanding to catch up with observation before clarity emerges from confusion. What we've learned is that universe still holds surprises, that our understanding, comprehensive as it seems within familiar contexts, remains incomplete when faced with genuinely novel phenomena. That institutional responses to extraordinary observations might not always serve our collective desire for knowledge and truth. That amateur observers and citizen scientists play a crucial role in democratizing space exploration, preventing complete narrative control by organizations that might have reasons, good or bad, to withhold information from broader populations. And we've learned, perhaps most importantly, that we must hold uncertainty without collapsing into premature certainty that relieves tension but might blind us to truth. 3i Atlas is either natural comet with unusual but explicable properties or something more, artifact, probe, messenger carrying information or intent we're only beginning to suspect. We don't know which yet. We might not know with certainty for years or decades or ever, but the not knowing itself is valuable, keeping us alert, keeping us questioning, preventing complacency that assumes we've figured everything out, when universe clearly still has lessons to teach. History will remember this moment, regardless of how the mystery resolves. Future generations will look back at our response to 3i Atlas as defining moment in humanity's maturation as spacefaring species. Did we handle ambiguity with grace? Did we maintain intellectual honesty in face of compelling but uncertain evidence? Did we balance skepticism with openness, avoiding both gullible acceptance of extraordinary claims and reflexive dismissal of genuinely anomalous observations? These questions matter beyond immediate scientific debate. They shape who we become as species reaching beyond our planetary cradle. The philosophical implications extend far beyond whether this particular object is natural or artificial. 3i Atlas forces us to confront how we respond when comfortable categories fail, when phenomena resist classification, when universe presents puzzles that don't yield to established methodologies. Do we expand our frameworks to accommodate new observations, or do we force observations into existing frameworks even when fit is poor? Do we admit uncertainty honestly, or do we pretend to certainty that data doesn't support because uncertainty makes us uncomfortable? These are not merely academic questions. They touch the heart of how science progresses, how knowledge accumulates, how civilizations grow wiser rather than simply more technically capable. The scientific method, for all its power and proven track record, works best when practitioners remain humble about limitations. When they acknowledge what they don't know with same rigor, they assert what they do know. 3i Atlas tests that humility, challenges us to say, "We don't know yet," when every instinct screams for resolution, for answers, for certainty that relieves cognitive tension. The institutional silence, whatever its motivation, serves as reminder that science is human endeavor, subject to all the political, social, and psychological forces that shape human institutions. Scientists are not purely rational actors, following evidence wherever it leads, despite idealized self-image. They're people with careers, reputations, funding pressures, institutional loyalties, and personal beliefs that shape how they interpret ambiguous data. Acknowledging these human factors doesn't diminish science's value. It contextualizes it, reminds us that scientific knowledge emerges from messy human process rather than descending from pure realm of objective truth. What happens next with 3i Atlas will depend partly on factors we cannot control: where the comet goes, what additional observations reveal, whether institutional gatekeepers choose disclosure or continued secrecy. But it also depends on factors we can influence: how we engage with ambiguous information, how we demand transparency while respecting legitimate needs for verification, how we balance wonder with skepticism, how we maintain curiosity without surrendering critical thinking. If you've stayed with us through this long night of exploration, if you've let these ideas wash over you in gentle waves rather than demanding immediate resolution, then you're practicing exactly the kind of patient engagement that complex mysteries require. You're demonstrating capacity to sit with uncertainty, to hold multiple possibilities simultaneously, to avoid collapsing prematurely into comfortable conclusions that might be wrong. That capacity will serve you well, not just for understanding 3i Atlas, but for navigating increasingly complex world where simple narratives rarely capture full truth. The story of 3i Atlas is not over, it's only beginning. As Comet continues outbound journey, as more observations accumulate, as institutional positions evolve and perhaps soften, we'll learn more. Perhaps we'll discover natural explanations for every anomaly, puzzle pieces that fit together once we have enough of them, revealing picture of exotic but natural comet from stellar system very different from our own. That would be valuable scientifically, expanding our understanding of planetary formation, diversity across galaxy. Or perhaps anomalies will deepen, resist natural explanation, even as data quality improves, force us toward conclusions we're not quite ready to accept. Perhaps we'll discover biosignatures suggesting life beyond Earth. Perhaps we'll find geometric regularities or electromagnetic emissions indicating technology. Perhaps we'll face moment when scientific consensus shifts from probably natural to possibly artificial, when extraordinary hypothesis becomes more parsimonious than accumulating stack of special pleading for natural explanations. That would be transformative historically, marking transition from cosmic loneliness to cosmic companionship, from assumption of uniqueness to acceptance of company among the stars. Either way, we're living through interesting times. We're witnessing interstellar visitors arriving with increasing frequency after billions of years of apparent emptiness. We're seeing astronomical communities grapple with phenomena that resist easy categorization. We're watching institutional responses to extraordinary observations that might, just might, force paradigm shifts comparable to Copernicus removing Earth from cosmic center, to Darwin connecting humanity with broader tree of life, to quantum mechanics revealing reality's fundamental strangeness. And you've been part of this exploration. By listening through this long night, by engaging with ideas that stretch comfortable certainties, by holding space for mystery without demanding immediate resolution, you've participated in collective human endeavor to understand our place in universe. That participation matters. It keeps a live spirit of curiosity and wonder that drives exploration, that pushes us beyond familiar boundaries, that makes us more than animals focused solely on survival and reproduction. Before you drift into sleep, before these ideas fade into dreams where logic loosens and imagination soars, consider subscribing to Stay Connected with this unfolding story. 3i Atlas is not done revealing its secrets, and neither is the broader exploration of our cosmic neighborhood. More interstellar visitors will come. More observations will accumulate. More debates will rage about what we're seeing and what it means. You'll want to be part of those conversations, to hear about new developments as they emerge, to watch as this mystery either resolves into natural explanation or deepens into paradigm shift. Hit that subscribe button. Join the community of curious minds who refuse to accept easy answers when complex questions demand better. Together, we'll track 3i Atlas's progress, analyze new data as it's released, interview scientists willing to speak honestly about what they're seeing and what they're uncertain about. We'll maintain that difficult balance between openness to extraordinary possibilities and grounding in rigorous evidence, between wonder and skepticism, between hope for cosmic companionship and intellectual honesty about what data actually supports. Turn on notifications so you don't miss updates when significant developments occur. This is living history, unfolding in real time, and you'll want to know when high-rise images finally appear, if they appear. When JUICE observations are released, when ground-based telescopes capture 3i Atlas's final brightening before it fades beyond detection range, when institutional positions shift or leak, when amateur observers detect something official channels aren't discussing. These moments matter, and you'll want to be there when they happen. Share this exploration with others who wonder about our cosmic situation, who look up at night sky and feel that ancient pull toward stars, who suspect that universe is stranger and more interesting than conventional wisdom suggests. These conversations about what we're seeing, what it means, how we should respond, need to happen broadly across society, not just among elite specialists. Everyone has stake in how humanity handles potential contact with cosmic others or discovers we're alone after all. Both outcomes shape our future in profound ways. Sleep well now. Dream of comets and starlight and vast distances between worlds. Dream of civilizations that might have sent their scouts across those distances to find us, to study us, to perhaps warn us of dangers we don't yet recognize. Dream of the day when humanity sends its own probes beyond solar system, when we become the visitors exploring other stars' planets, when we're the mysterious strangers appearing in alien skies, raising questions about natural versus artificial, about coincidence versus design. And when you wake, the mystery will still be here, waiting with patient persistence that cosmic phenomena excel at. 3i Atlas will still be moving through its hyperbolic arc, counting down days until it passes beyond our observational reach forever. The questions we've explored tonight will remain unanswered but not forgotten. Seeds planted in minds that might bloom into understanding as more data emerges as patterns clarify, as truth, whatever it turns out to be, gradually reveals itself to those patient enough to watch without demanding immediate resolution. But you won't be alone in that watching. You'll be part of community, connected through subscription, sharing observations and insights, learning together as mystery unfolds. That community matters. It's where individual curiosity amplifies into collective understanding, where different perspectives illuminate aspects single viewpoints miss, where amateur and professional, skeptic and believer, scientist and philosopher can engage in dialogue that enriches everyone involved. The stars keep their secrets well, but they don't keep them forever. Every secret eventually yields to patient observation, to careful reasoning, to cumulative effort of minds working together across time and distance. Three-Eye Atlas's secrets will yield too, in their own time, in their own way. We just need to be there, watching attentively, thinking carefully, remaining open to whatever truth reveals itself while maintaining standards of evidence that protect us from comfortable delusions. Good night, traveler. May your dreams carry you safely through the darkness, and may you wake ready to face whatever revelations tomorrow might bring. The universe is stranger than we imagine. Perhaps it's stranger than we can imagine. But we're learning to ask better questions, to look more carefully, to accept mystery without surrendering curiosity. And that might be exactly what we need for whatever comes next. Subscribe now. Join us. Be part of this journey as it continues to unfold. Because Three-Eye Atlas is just the beginning. The cosmos has more stories to tell, more visitors to send our way, more mysteries to present for our consideration. And together, we'll be ready to receive them with wonder, tempered by wisdom, with curiosity grounded in evidence, with hope balanced by honest acknowledgement of what we know and what we're still learning. The dawn breaks, a new day begins, and somewhere above, beyond atmosphere's protective embrace, an interstellar visitor continues its ancient journey, carrying secrets we've only begun to glimpse. Sleep well. Tomorrow, we continue watching.